Good morning, dear students.
Good morning,
Good
sir.
morning, sir.
So, in the last lecture, we have discussed the PDB work for various quasi-static processes. So, these processes are the thermodynamic processes. So, for each of the processes, we should know how to find out the work done. So, today we will going to solve some problem on the first law of thermodynamics. So for any process, mathematically, we can write by the first law that del Q, difference of the heat, del Q minus del W will be equals to dE. Okay, so this basically means what? Suppose one very hot body, okay, suppose one very hot metallic body, it is moving on the floor, and you are just doing some work, and you are restricting the ball and you are stopping it. So what will happen? So the ball will stop, isn't it? One very high velocity ball, when it was, or moderate velocity ball, when it was moving on the floor, and when suddenly it is stopped, so what will happen? So some heat will generate and it will stop, means due to work application the ball will stop and the temperature will rise. Okay, so for that process, so it is delta Q minus delta W is equals to dE. Okay, and dE is what? This is change of energy. So this definition or this expression can be related to any of the thermodynamic process. Though the thermodynamic laws, the first law, so it is basically stated for a cycle, but mathematically for a process, so we can write like this way. Okay, suppose in one piston cylinder arrangement some gas is there, so which is our system. Let's say some heat is added, or let's say the cylinder is heated. So due to the application of heat, if the boundary of the system it is displaced, or the piston it is displaced, then some work will be done due to the application of heat. So that for that process, so you can also this formula. Okay, means for any process we'll be using this formula. Okay, and for any cycle, so we will be adding up all the work, which will be equals to summation of all the heat interaction, but that is for a cycle, this is for a process. So here E is basically the energy, total energy of the system. So in most of the cases, this E we will be writing D capital U, because U is the internal energy. So capital E, it is basically composed of three kinds of energy: internal energy, kinetic energy, and potential energy. So the effect of this internal energy is more. That is why sometimes instead of D, we will be writing D of U, capital U, means the difference of the internal energies. Okay, so this is one process. So by this way, so you will be able to write the first law for this process. Understood? Okay. So by applying this process, we will be solving one or two problems today. But before that, I want to just discuss with you two important things. One is the what will be the energy of an isolated system. So what is an isolated system? So basically the system, it is divided into three categories. One is the closed system or control mass system. Second one is the open system or control volume system. Third one is the isolated system. So by the definition of isolated system, the system which doesn't interact any mass or energy through its boundary with the surrounding, that system is called as isolated system. So if it does not allow any transfer of energy, means if it does not allow the transfer of heat and work, so there will not be any change of heat for closed system. There will not be any change of work. Yes, because there is no energy interaction. That is why delta W will be equals to 0. Means these are the two basic forms of energy. That is why there is no transfer of energy. Yes, because there is no transfer of energy. So these two terms will be equals to 0. So the first law gives, so delta E D equals to 0, isn't it? So delta Q minus delta W equals to D. So as the other two terms are 0, that means what? D also 0. So if differentiation of any term is equals to 0, so that means that parameter is in constant parameter. Okay. So D equals to 0 means E equals to constant. Means what? The energy of an isolated system is always constant. So you need to remember this point. So the energy of an isolated system is always constant. So if you are asked to prove it mathematically, then this is the logic. Okay, as because there is no transfer of energy through each boundary, that is why delta Q will be equals to 0, delta W will be equals to 0. That means by first law, so D equals to 0 because delta Q minus delta W will be equals to D for any process which will be occurring in isolated system. Understood? So finally you will get E will be equals to constant. Okay, so what is E? E is the total energy. Okay. Now there is one important terminology actually. That is PMM. PMM means perpetual motion machine. So what is that machine? So what we have actually come across, that energy is neither created nor destroyed, but only gets transformed from one form to another. So this is the basic first law actually, or first principle of energy. Okay, so energy is neither created, it is only or not destroyed, but it can be transformed from one form to another. Means work can be transferred to heat, heat can be transferred to work. So energies are transforming, okay, or it can be transformed. So you cannot build one machine. Suppose this is one machine, so this is one block diagram. This may be your motor car machine, or this may be your motor vehicle bikes machine, okay, bike engine. So you cannot produce work W without the expenditure of equivalent amount of heat. Means from an engine, without giving any kind of source resources, okay, just heat. You can take the example of coal. So if you do not heat, you cannot produce work. Means what? If you are getting work, that equivalent amount of heat you need to introduce to the system. If that happens, that without introducing any external energy, you are just producing work. So if that thing happens, that imaginary machine will be called as PMM1, means perpetual machine motion machine 1. Okay, so see, there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. Okay, so if that can be happen, which is the uh, uh, actually false statement. Okay, so if that can be happen, then that machine will be called as PMM1 machine. Okay, so these machines are imaginary machine. You cannot get soul effect as work without the expenditure of any other form of energy, that is heat. Okay, that is why, so some energy should be given to the system, then only work will be uh, work will be got as an output. Okay, so such fictitious machine is called perpetual motion machine of the first kind, or in brief PMM1. Okay, and reverse is also this is also impossible. That is, the converse of the above statements is also true. Okay, that means what? There can be no machine which should continuously consume work without some other form of energy appearing simultaneously. Okay, so if work is not consumed, so it cannot produce heat. Okay, means automatically some form of energy cannot be evolved from a machine. Okay, so there must be some other form of energy which will have to be interacted to the system. Okay, so if that happens, so it is an imaginary machine, and that imaginary machine is called as PMM1 machine. Understood? Okay, so after these two things, so we can just apply the first law of thermodynamics to a system. Okay, so we will take one numerical problem. Okay, so before that, I want to uh, actually have a feedback from you that are you getting what am I teaching your students?
Yes, sir.
Okay, yeah, don't take it in a complex mode. Okay, so all the things are having some practical application. So though the theory is little bit, sometimes little bit it may be confusing, but when you will solve some problem, so as we are doing today also, so then I think when you will practice the problem, your concept will be clear. Okay, so whatever we have covered in theory, so that things will be clear to you. Okay, so let's take that example. See, the language of any problem, it may be some lengthy, okay, language, but the things are simple. Just read the question. A stationary mass of gas is compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to a final state 0.15 meter cube and 0.105 megapascal. Means two states are given for a gas. So here gas is the system. So which will be in a piston cylinder arrangement. Let's say piston cylinder arrangement. So that gas, that piston will be having some friction. Okay. So when yeah, the initial state of that gas is what? The volume is given, initial volume is given. This is P1, 0.3 meter cube, and the initial pressure is given. Point P1 is 0.105 megapascal. So initial volume is given, initial pressure is given. So by this pressure and volume, the state it is defined for the gas. Okay. Now the final volume and the final pressure is given. Means this is P1, this is P2. Sorry, this is P1, this is P1, this is P2, this is P2. Okay, simple. So we are given P1, B1, P2, V2. Okay. Now the pressure remaining constant during the process. Okay. So when this was happening, you can see P1 will be equals to P2. That is what it is written. The pressure remaining constant during the process. Means when the system of the gas reaches from state 1 to state 2, this P2 V2, the pressure was constant. Means what? That is one process, thermodynamic process. Okay. Now I think you are clear that what is a process. Okay. Now there is a transfer of 37.6 kilojoule of heat from the gas during the process. Means in any process, I have told you that in any process there may be interaction of energy. So that energy can be of work energy, or that energy can be heat energy. Okay. So this is one process, thermodynamic process, just like this process. This is process. So here the pressure is changing, but in our problem the pressure is not changing. Okay, I want to show you if it is there. I don't know. Pressure, constant pressure process. Yeah, you can take this example, constant pressure process. So this is state 1, P1 P1 is given, and P2 P2 is given. So P1 and P2 are same, Pi and Pf are same. Okay. So in this process, so work is there. Okay, work is given. So there is a transfer of 37.6 kilojoule. So kilojoule, joule is the unit of energy. So the work and heat are having the same unit as that of energy. So here one important thing, 37.6 kilojoule of heat from the gas. Means from the gas we are getting what? 37.6 kilojoule of work. That means what? That work will be positive work. So when we'll be applying it in the thermodynamic, this law, first law of thermodynamics, so we will be writing it as positive work. Okay, because 36.5 will be the positive work. How much does the internal energy of the gas change? So in this process, okay, in this process, so how much means what? This is one step, this is another. P1 P1 is given, P2 P2 is given, though P1 is same. So in this process the work interaction is given, means work is evolving. Okay, means it is positive. So in this process, so what will be the change of internal energy? Okay, how much does the internal energy of the gas change? So very easy. So for this process, what we will do? So we will be applying the first law of thermodynamics. And what was the first law of thermodynamics? Delta Q minus delta W equals to D. So for this process, so we will be applying this concept. Okay. So directly here it will be U2 minus U1, isn't it? Because internal energy we need to find out. See, what is the first law for a process? So first law for a stationary system in a process given by Q equals to delta U plus W. You can write Q minus W equals to delta U, or you can write Q equals to delta U plus W. Okay. So what is Q1 to 2? Means from state 1 to state 2. So U2 minus U1, because delta U is what? Final internal energy minus initial internal energy. U2 minus U1 plus W1 to 2 for process, because there is only one process, process 1 to 2. Okay. So we will have to write like this: 1 to 2, U2 minus U1, W1 to 2. This is general form. This is the form for our problem. Okay, so as there is only one process, so we are writing this formula. Now we will be putting the values what they have given. Okay, so now see here, W1 to 2, W1 to 2 means what? Means this is the displacement work. Okay, as because the volume has changed from this to this, so we can find out the displacement work W1 to 2. So how you will be finding this displacement work? So W1 to 2 will be what? This is a PdV work. So P1 to P2. So P value is given because it is constant. P2 and V1 volumes are given. Okay, means these values are given. So here we will be putting, and finally we will get that W1 to 2 will be equals to minus of 15.75 kilojoule. Okay, minus of 15.75 kilojoule. here this was not work. Okay, here this was the energy in heat form. Okay, 37.6 kilojoule of heat. So this expression we have found out W1 to 2. This is given. Q1 to 2 is given. So if this is Q, means the heat is evolving from the system, it will be negative. Okay, I am very much sorry, because earlier I have told that this is work. This is not work transfer, this is only heat transfer. Here is a transfer of 37.6 kilojoule of heat from the gas. So if heat is evolving from any system, here it is negative. Now we are having this value, it is given. We need to find out U2 minus U1. W1 to 2 we have found out by this displacement work. Okay, for constant pressure process. So for constant pressure process, this is the formula. In the last class we have seen the formula. So this is minus this one. So Q1 to 2 it is given because heat is evolving, it is negative sign. Okay, so in the formula, in this formula, so 1, so we'll be putting all the values. So minus 37.6 equals to U2 minus U1 minus 15.75. Q equals to U2 minus U1 plus W. So for W it is negative. So that is why U2 minus U1 will be minus 21.85 kilojoule. Okay, means what? The internal energy of the gas decreases by 21.85 kilojoule. Understood? Students? Rishikesh? Nilotpal? Nausal?
Sir.
Nausal? How are you finding this problem? Is it okay for
Yes,
you?
sir. It's okay,
Okay,
sir.
very simple thing. Okay, don't get confused. Very simple thing. This is the simplest form of any problem for this course. Okay, now I'll be taking another problem. This is a combination of processes. Earlier in this process, there was only one process. Okay, now there are so many processes. You can see this is one cycle. So you can apply first law of thermodynamics to the cycle as well as for each of the process. So for a process, so how we will be using the thermodynamic first law, we have already seen. Okay. So by using all those things, so we can find out what they are asking in this problem. See, this is a very lengthy actually question. So, but the concept it is here behind this question. So you should know how to solve this problem. So when a system is taken from state A to state B. This is state A, this is state B. These are also states C and D. State A to state B, it through path ACB. ACB. There are three paths ACB, then directly A to B, okay, or B to A because arrow mark is given in this direction B to A, and ADB. Okay, so in ACB, 84 kilojoule of heat flow into the system. Heat flow into the system will be positive. Heat flow out of the system will be negative. So 84 kilojoule of heat flow into the system. So when the path is this one ACB, so 84 kilojoule of heat flow into the system, and the system does 32 kilojoule of work. Means in going by this path, the total heat interaction is 84 kilojoule and the work is 32 kilojoule of work, and the system does means that is positive work because the system is doing some work. You are getting work from the system. So 32 kilojoule of work. So in ACB, what are the given things? Q is given and W is given, or it means Q ACB is given or W ACB is given. So we will write in the question. See, Q ACB is given, Q W ACB is given. In this part, both the things are given. Now, in A, they have asked how much will the heat that flows into the system along path ADB. Means in ADB, how much uh, heat will flow into the system. Work done is given. In this part, the work done is given as 10.5 kilojoule. Okay, so here heat is not given, work done is given. So by looking at this figure, so what you can actually conclude, see, because the work and heat are part functions, so the values of work and heat Q and W will be different in each of the parts. So if you go by this part, Q will be different, W will be different. If you go by this part, Q will be different, W will be different, means that will be different from this part. Okay, and if you go by this part, the Q will be different, W will be different, but one thing will remain constant. Okay, that is why we can write the first law of thermodynamics. What was that? So energy was, that difference of energy in between these 2 points was constant, isn't it? So we have seen, and that difference is called as the total energy of the system, isn't it? Means Q minus W, that is a constant term, that is delta E. Okay, so difference of internal energy, it is constant. Okay, so we will be applying that concept in each of the part. Okay, so here when the system return from B to A, so from B to A, if the system returns to the curve path, the work done on the system is 21 kilojoule. Work done on the system means it is negative. Okay, does the system absorb or liberate heat? So they have asked that the heat is evolving or it is absorbing, and how much of heat it is absorbed or liberated. Okay, so we will come one by one. So first we will take this one. So how much will the heat that flows into the system along path ADB? So for ACB, all the things are given. Q is given, W is given. For ADB, W is given, Q is not given, and you are asked to find out Q. Okay. So for this process, so what we will be doing? So QACB is what? QACB for part QACB, means for part ACB, how you will be applying the first law of thermodynamics. So QACB will be equals to delta U plus W, means delta U is what? Final state is, final point is UB. So UB minus UA for this part. Okay, for this process, UB minus UA plus WACB. Okay, so WACB. So WACB it is also given because work done on the system. Okay, so it will be 30, oh sorry, it is work done by the system. Okay, so UB minus UA will be what? 84 minus 32, because QACB is given 84, and this is also positive, work done by the system. So 84 minus 32 will be equals to 52 kilojoule. Understood? So UB minus UA it is found out, means the difference of the internal energy it is found out. So for any part, that difference will be equal, isn't it? Because that is the property of the system. Okay, internal energy is the property of the system. So from this to point this, so whatever be the part, that difference, this 52 kilojoule will be constant. Now you can able to find out the heat which will be flow through this part ADB. Okay, so for QADB, how we will be writing? Final UB minus UA plus WADB. So WADB. So WADB it is given 10.5, as because the system is doing some work, it is positive. And UB minus UA, I have told you that in between these 2 points, whatever path you will follow, that is constant. So UB minus UA will be 52, because we have found out UB minus UA will be equals to 52. Okay, so this is 62.5 positive. Okay, means some heat it is supplying, we are supplying some heat to the system because it is positive. Okay, so by sign convention you can conclude that thing. Now what is asked in B, when the system is returned from B to A, from B to A along path, along the curve path, the work done on the system is 21 kilojoule. The work done on the system means this is minus 21 kilojoule. Okay, by following the sign convention, W will be negative 21. So does the system absorb or liberate heat, and how much of the heat it is absorbed or liberated? So we will be applying the first law for this process. So Q, what I will write, Q BA, you can write Q BA will be equals to UA minus UB plus W BA. See Q B to A, Q the UA minus UB. Final point is A because arrow mark is given this way. Okay, UA minus UB plus W B to A. Understood? So this is what UA minus UB. UB minus UA is 52. So UA minus UB will be minus 52. Okay, and WB2A is minus 21. I have told you because system is not doing this work. System we need to do some work on the system, so it will be negative. So finally you will get minus 73 kilojoule, means 73 kilojoule of energy it is evolving from the system. Okay, so just like the exothermic reaction, when heat is evolved, so it is given negative sign. So here also negative sign it is given. So system leverage, okay, or system this much heat is evolved from the system, or system leverage this much of heat, this kilojoule of heat. Understood? So no need to write here negative because liberated already written here. Okay, now in C what it is asked, if UA equals to 0, means this equals to 0, they are saying, and UD equals to 42 kilojoule. Very important, okay? Just concentrate. Please be concentrate. Then only you will get this concept. UA equals to 0, UD equals to 42. And here UD equals to 42 kilojoule. Find the heat absorbed in the process AD and DB. AD and DB. Okay, so you need to find out the heat which was absorbed in the process ADN DB. Total heat was given. Total heat was, we have found out what was the total amount of heat, but they are asking to find out what was the heat interaction in the process AD and in the process DB. So how we will be solving that one? We will be writing WADB, means whole process we will be writing WADB. So it will be composed of WAD plus WDB, isn't it? WAD plus WDB means this work plus this work will give you the WADB work. So what is PDB work in this AD process? So it is given in the question. Okay. So AD, what is DB? What is DB? So DB will be what? This is a constant volume process. You can see this is graph in between P and V. This is constant volume process. So WdV will be equals to 0 because in the last class we have found out that for constant volume process, as because there is no change of volume, the work done, BdB work will be equals to 0. That is why WAdB will be equals to WAD. Understood? WAdB will be equals to WAD, and this is given as 10.5 kilojoule. It is already given. Okay, so you can find out QAD. So by applying first law, QAD is what? QAD will be what? UD minus UA plus WAD. So that is given. UD is 42 kilojoule. It is already given. Okay, 42 minus 0 because UA is 0 and 10.5 it is given. This much of heat that you need to supply to the system, or the system will absorb this much of heat. So QADB will be what? 62.5 kilojoule. Understood? Because this much of heat you need to add. Okay, so QADB will be this one, QAD plus QDB. So QDB will be what? QDB will be 62.5 minus 52.5. So 10 kilos. Understood? So this way you need to solve some problem on first law of thermodynamics. Okay. So what you need to do? You need to take one pen and paper. Okay. And you need to see the problem. Okay. You need to read the problem very carefully. Okay. Step by step you will be writing each one of the things which will be given and each one of the law on the side, first law, okay, the mathematical expression by taking all these things. So just you can solve some of the problems. Okay, so these problems are not that tough, but you should know each and everything, each and every small things, that what will be the work done for constant pressure process, what will be work done from for constant volume process, for adiabatic process, for polytropic process, isobaric process, isochoric process. Okay, so all those terminologies and all those formulas you should commit to your memory. Okay, I think, dear students, you have got the practical concept, okay, of this first law of thermodynamics, how we have actually used this formula, okay. And today's lecture is very, very important, okay, and then only you will be able to apply the first law to any process. So if you have any doubt, you can ask. I will be sharing this PDF file. In the last class also, I had used one PDF file that will be also, I will share, okay, in the Google Classroom. So you just go through it. If you find any difficulty, you can ask. So for this today's lecture, if you have any doubt, you can ask. Okay, those who do not have any doubt, they can leave the meeting. Thank you, dear students.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.